Thanks very much for inviting me. So I'm Wesley. I'm from the CNRS in France. I'm based at the Archives Henri Poincaré in Nancy. But I used to be at the LSE, so maybe if anybody has heard of me, that might be how. But today I'm going to talk about this question of whether true AI is mathematically impossible or not. The answer will be inconclusive, just so nobody gets their hopes up. So the you've probably all heard in the news about this idea of tech companies trying to solve math in some way. Lots of money has gone into this project of AI mathematics to try and get AI to copy human mathematicians at various levels. So the moment there's been some success at the lower levels, so you probably all saw this in the summer at the various AI programs won gold medal on the IMO problems. So these are, if you don't know about these, they're extremely hard problems that are very difficult to solve, but they only use like high school level maths. So this is pretty impressive, but of course it's not good enough for the Silicon Valley people. They want more, and there are several serious projects underway with big name mathematicians to get more kind of AI mathematics going. So people are working on various different aspects of this and coming at it from different angles, but Tim Gowers is working on this, Terence Tao is working on this, Kevin Buzzard is working on this, so there's real interest in this, not just from the Silicon Valley people, but also from mathematicians themselves. It seems like the goal of this research is to just write computer programs that can autonomously simulate the research activity of professional mathematicians. So people are now starting to get worried that this is going to effectively put mathematicians out of a job. So this is something that people are beginning to get worried about, but still, while it's only at IMO level, it's for a few years maybe. So this is something that people are quite interested in these days. But actually, there's been a sort of line of thought in the sort of philosophy and logic literature for around 60 years that this is actually just impossible. That it's somehow mathematically impossible for anybody to create a computer program that can simulate human mathematics in its entirety. So this is actually, it's quite an old topic, but it seems to have become, recently much more relevant. I guess nobody had to really worry about this stuff in the 60s, but now maybe we should. So that's the sort of background to the talk today. There's probably going to be a bit less maths than you would normally have, but there's some logic and some philosophical thinking about it. So the talk today is going to be focused around Gödel's incompleteness theorems. So these are probably the most significant results in mathematical logic. Some of you might know what they are. Some of you might have just heard of them in some way. But they're clearly very important results. But unlike most sort of theorems in mathematics, people keep thinking that they have these really important philosophical consequences. Right? So people have argued that Gödel's theorems tell us, these are just theorems about axiomatic formal systems, but people have thought that they tell us all sorts of other things about the nature of reality and truth and so on. Myself included, so I don't say that disparagingly. I've written about some of this stuff myself. But one of the philosophical consequences that Gödel's theorems apparently have, and this is the one we'll be talking about today, is anti-mechanism. So this is the view that no computer algorithm can simulate all the mathematical reasoning that humans are capable of. So apparently this follows from Gödel's theorem. This has been claimed by a few people, and that's the claim we're going to investigate today. So three things to get through. The first is just to explain the incompleteness theorems somewhat. So this will be dull for anyone who already knows what they are, but just in case people don't, we'll have a quick look at Gödel's first incompleteness theorem. So you only need the first one to get this anti-mechanist sort of argument going, and in fact you don't even need the first one in full generality, you just need a sort of simplified version of it. So we'll look at exactly what that is first. Then we're going to look at Penrose's anti-mechanist argument based on Gödel's incompleteness theorem. So you may know Penrose from him having a Nobel Prize in physics, but another thing he's less well known for, but still quite well known for, is this kind of anti-mechanist argument on the basis of Gödel's theorem. So we'll look at his argument, And then the last thing I'm going to do is try and say why I think the argument doesn't work. So I suppose we're not going to get entirely to the bottom of the question of whether AI is mathematically impossible, but I think at least probably the most persuasive argument that it is mathematically impossible doesn't work. So there's some reason to fear, I suppose, or rejoice, depending on whether you work in the university maths department or Silicon Valley Tech. So Gödel's theorems are not directly anything much to do with computers, but the link is fairly easy to establish once you've seen what the theorem is. So initially, we're just going to think about formal theories of arithmetic. So these can be characterised more precisely, but we don't really need all of the full bells and whistles definitions. The first thing to note is just that formal theories are always given in a precisely specified formal language. So of course, if you open up your number theory textbook, it's going to be some English and some equations and a sort of hybrid of technical and natural language. Formal theories are just always written in a precisely specified mathematical language of the sort that you can program in on your calculator, if you have a calculator. Maybe young people don't have calculators these days, I don't know. But you can do it on your phone. But a formal theory has a precisely specified language and then two components. So the first is the axioms. So these are your starting assumptions of the theory. In theories of arithmetic, this is often fairly simple stuff, like the definition of addition and multiplication, and piano arithmetic, which is the standard formal theory of arithmetic, also includes an axiom for mathematical induction. But these, strictly speaking, can be whatever you like. They're just whenever you're doing a proof with an axiomatic formal theory, you can write down an axiom whenever you like. You don't need to prove them. And then after that, we have the theorems, which are just all the other formulae that can be derived from the axioms by applying your proof techniques over and over again. So obviously, for all this to work, it needs to be precisely definite what the axioms actually are. So you can do that by just having an explicit list of the formulae that get to count as axioms, or you can define the class in some way, but it's got to be done precisely. You're not allowed to say things like, all the axioms are just what I'm thinking of now. This needs to have a formally correct definition, and we need a formal logic to specify exactly what inferential moves are allowed when deriving theorems from axioms. But that's the general picture. Gödel's theorem is about these kind of theories, which are axiomatic formal theories in a formal language with a formal logic. So that can all be defined properly, but it's fairly tedious and not really necessary for the argument. What will make a formal theory a theory of arithmetic is one in which we can either carry out basic arithmetic directly, so the language will include symbols for the successor function, the addition function, multiplication, and so on, or it might be a more powerful theory in which you can simulate arithmetic, like set theory. So obviously set theory doesn't talk about numbers directly, it just talks about sets, but you can sort of define some sets that are isomorphic to the natural numbers and operations that behave in that kind of way. So this is any theory which is suitably formal and which you can either do basic arithmetic directly or by proxy. So these are the kind of theories that Gödel's theorem applies to. And we're going to say a theory is sound just in case all of the axioms are true. So you can pick any statements you like for your axioms, but if you pick false statements, the theory is not sound. And obviously, if your formal logic is truth-preserving, this will mean all the theorems are true too. So that's the sort of thing that Gödel's theorem is about. The theorem itself is surprisingly kind of simple idea behind it, but it's also very weird. So the basic version of the theorem that we're going to need for today, although you can make the theorem a lot more general than this, but the version that we need is that no sound theory of arithmetic can be used to derive all the true formulae of arithmetic. So there's just no way to set up an axiomatic formal system in such a way that you can derive all and only the true formulae of arithmetic. So obviously there are some, you might think, can I just cheat and say that all the axioms are all the true formulae of arithmetic? Yeah, you can, but then the theory is not formal in the right way. So effectively, if it's the sort of theory that can be dealt with by a computer, which will be relevant in a second, then there's no way to make the theory sound and complete in the sense of deriving all the arithmetical truths. And this is Gödel's theory. The proof is extremely long and involves lots of very fiddly formal verifications, but we can talk about the basic idea in case anyone's unfamiliar, which I expect might be most of you. But the basic idea behind the proof is to use Gödel numbering. So the idea is that the formal language and the formal system of logic is precisely defined and well behaved. So we can encode information about the theory of arithmetic into the language of arithmetic. So you can talk about the theory's formulae and inference rules and so on by talking about natural numbers by proxy. Yeah?
I'm very sorry to interrupt.
No, that's fine.
If you go back to the previous slide,
Yeah.
I thought that axioms are like sort of defined as like truthful statements.
Oh yeah, okay. So there is a sort of traditional usage going back to like Euclidean geometry and those other sort of early axiomatic systems, where an axiom is supposed to be some sort of self-evident basic truth, and the idea is that when you're doing your Euclidean geometry or something, you don't have a proof of the axioms, but that's fine because you also don't need one because they're just blindingly obviously true. So this sort of technical usage of the term is not quite the same as that. So in sort of modern axiomatic mathematics, the axioms are like traditional axioms in that you are allowed to use them at any point without proof, but they're generally regarded as being sort of arbitrary statements that you pick out. So of course there's a question: is a theory going to be interesting if it has false axioms? And probably not. But there's no. So normally when you come up with a theory of arithmetic, you are only interested in the sound ones where all the axioms are true. But there's also no particular requirement that they have to be self-evident, and especially when we do, if you're doing this with set theory, right? Set theory contains axioms that are, it's a bit of a stretch to call them self-evident. So you may have heard of like the axiom of choice or something. It's not an axiom in the traditional Euclidean sense, but it's an axiom in the sense of like everyone just assumes it and we go from there. So so this is maybe slightly misleading with respect to the more kind of old-fashioned terminology, but from from around sort of 1900, this new use of just the axioms are just your starting formulae effectively. That's the usage we make. But yeah, good question. But of course, if you want to think of the axioms as truths, from now on you're welcome to do that because we're only going to be thinking about sound theories. And it's a good question. If we think this is an issue we'll come back to later, but you can sort of do derivations in a formal system even if all the axioms are false, right? And it's like a nice little puzzle, like a Sudoku or something, just applying the logical rules to try and get some form of statement. But you won't really be having you won't be producing like a proper mathematical proof that should convince you of the conclusion. But we'll come back to that later. But this is the basic version of the first theorem then. So if you've got an axiomatic theory which does have this nice feature that all the axioms are true, you'll never be able to derive all the true formulae of arithmetic from it. So Gödel numbering, as I said, we have this idea of using the language of arithmetic to encode syntactic information about the theory. And in particular, we can formulate a Gödel sentence. So if T is some suitable formal theory, G of T, which is T's Gödel sentence, it encodes the assertion that there's no derivation of G of T from the axioms of T. So this might look a little bit like self-reference somehow, and this is often described as, G of T says that it's not provable in T or something. It's not strictly self-reference. So G of T is just an ordinary arithmetical assertion. If you were to write it down, it would probably just look like horrible, complicated, nonsense. But this would just be an ordinary arithmetical formula, but under the coding system, it encodes the assertion that there's no derivation of the Gödel sentence from the axioms of T. So the idea behind the proof of Gödel's theorem, as I said, the real proof is very complicated, but the sort of sketch of the proof is very quick. So if you think of what's the relationship between T and its Gödel sentence, well, if T is really sound, it only proves true formulae. So suppose there is a derivation of T's Gödel sentence in T. well then the Gödel sentence has got to be false, because the Gödel sentence encodes its own sort of non-provability in T. So if it were provable, T would prove something false, and we know that's ruled out by the assumption that T is a sound theory. So this is a weird idea, but hopefully that makes sense. So we know that G of T can't be provable in T if T is sound, but that's exactly the assertion that's encoded by G of T. G of T effectively asserts that it's not provable in T. So if T is sound, then its Gödel sentence is a true formula of arithmetic that's not provable in that theory. So obviously you really do need some hard work to show that actually we can do the coding correctly and all the rest of it, but it works out. The other thing that's really important to note is that the name is a bit misleading. So this should really, I think, be called something like an incompleteness theorem. So you might think, well, if we just can't prove the Gödel sentence, maybe we could add the Gödel sentence as a new axiom and just have a stronger theory, which would be T plus its own Gödel sentence. But then that just gives you a new axiomatic theory. The axiomatic theory is going to be sound, because T is sound, and all we did was add one new axiom in, which we've already worked out must be true. So then the stronger theory, which you normally would write with the slightly weird use of the addition symbol, so this would be sort of T plus G of T, or something. Sorry, that's illegible. I'll get a new pen. But that theory would meet the conditions for Gödel's theorem to apply to it, and so it would just have a different Gödel sentence that it can't prove, and you wouldn't have really made the theory any less incomplete. So this is a sort of crash course in Gödel's incompleteness theorem. So this is the first one. And as you can see, there's nothing sort of explicit about computers in there, but apparently this motivates the anti-mechanism argument. So all on board so far? I have to take a quick question if there's need for clarification. Yeah.
Sorry. I was just wondering, what are we basing our judgment of truthfulness of something if it's not axioms? I thought we used axioms for that.
Yeah, this is a good question. So this sort of issue will come back up later. But the basic idea is we're just using the notion of truth in the totally ordinary sense, right? So if from your axioms of arithmetic you can derive 2 plus 2 is 5, something you've derived a falsehood, something's gone wrong. So it's a really good question, and we'll discuss that in a bit more detail later. But the intention is just for truth to be used in the ordinary sense. And certainly, when we're thinking about set theory or something, maybe we're starting to stretch the notion of truth in an ordinary sense. But for arithmetic, it just seems like if you write down a formula of arithmetic, it should be either true or it should be false. And maybe you need axioms to prove it one way or the other, but the default assumption, at least, is that it's just got its truth value independently. Yeah.
So how would you if truth is based on the ordinary truth, then how do you verify statements about more abstract mathematical objects?
Well, it depends what you mean by sort of verifying them. So, in the more abstract branches of mathematics, sometimes the axioms will effectively just be definitions. So, for example, in group theory or something, you just stipulate what a group is, so there's no real question about something false happening there. I mean, typically, if you're thinking of all of this as working in, say, set theory or something, you will give an interpretation of the axioms of your abstract theory in set theoretic terms, and then you can manually verify that all the axioms hold, and that can be quite a lot of hard work. But then you know that if anything that you can derive in the set theory, if you translated it sort of back into the original abstract setting, would also be true, assuming, of course, that set theory is consistent and everything. So it's a good question. It's not totally straightforward. Is the answer, but in principle, if you sort of already think that your axioms for your whatever area of maths you're doing are true, then you can render them set theoretically. Good. All right. So that's the first incompleteness theorem, and we'll come back to this truth issue later. How it connects to the AI issue. So there'll be some hand waving here, but you'll be able to see what's going on. So let's suppose that C is some computer that simulates arithmetical reasoning. Very roughly, what's going to be going on is that you give C a class of input formulae. C will repeatedly apply some operations to those formulae according to an algorithm, because it's a computer, and it will produce a class of formulae as the output, based on that particular input, as dictated by the algorithm. So what this means is if we leave our computer running indefinitely, so it just keeps churning out formulae, its output is going to match exactly the theorems of some formal theory of arithmetic. So effectively, there is basically a correspondence between the formal theories in the sense that we were just talking about and Turing machines. So for any formal theory, you can program a Turing machine to just print out all the theorems of that theory one by one, leaving it to run forever. And likewise, for any sort of computable output of a Turing machine, you can represent that as the theorems of a theory. So effectively, just because a computer is applying sort of formal operations, there's no problem translating Gödel's incompleteness theorem to a statement that's about computers, or at least about Turing machines. So somewhat anthropomorphizing, we can say that C, some theorem-proving computer, proves all and only the theorems of the theory which its operations encode. So if C only proves true formulae, then it doesn't prove the Gödel sentence of the theory to which it corresponds. So this is the connection to Gödel's theorem, and the connection to AI more generally. So if you're programming, AI model to produce mathematical formulae, presumably you want it to only say true things, and if you do, then you know there's going to be some true thing that doesn't get proved by the system. So this is the connection. So Gödel's theorem puts a very firm limit on what's provable by a computer. So the idea behind these anti-mechanist arguments is to somehow show that if humans don't share this limitation, then whatever humans are doing and whatever computers are doing when they do mathematics have to be different things. So the strategy is to somehow use this result about what computers can't do to show that the human mind can't be simulated by a computer, even for something like arithmetic. And maybe you already believed that the computers wouldn't do a good job of art or something, but even for arithmetic, apparently people have thought that they can show that the mind is not a computer. So that's the basic sort of logical setup for things. And of course, we've got to be careful, right? None of this would mean that we can show that somehow human mathematicians are superior to computers. Right? Computers are going to be faster, and they have more memory, and are going to make fewer mistakes, and so on. But the idea is we're going to try and use this to show that there's something that we'll be able to prove that computers can't prove. So there's no danger of everyone being out of Gödel. So quite a few people have thought that Gödel's theorems imply that the mind isn't a computer. Gödel thought it, but didn't really publish anything on it, unfortunately. And then since Gödel thought this thought, several other people have tried to fill in the details of the argument. So there's the two famous versions of it are by Lucas, who is a philosopher. His argument isn't that good. It's been pretty thoroughly trashed in the literature. And then Penrose comes along, and he has a much better argument. So he has several arguments, and his first one is very similar to Lucas's, and it doesn't work, and we're not going to bother with that today. But in this book, Shadows of Mind, which you may have heard of, it's from like 1994 or something, he has what he calls the central new argument, which is much better than the first one, and that's what we're going to look at today. So part of the goal is just to get clear on exactly what this argument is, because it's not clear from the book. So I don't know if anybody has tried to read this, but the argument occurs in multiple different places and it's different every time it appears. So it's not, it's not 100% clear what's going on. So I'm going to try and reconstruct the argument in the best possible way, and then we can see what goes wrong with it. So here's the general structure of the argument. If I can find a pen that works, I'm going to try and note this down here as well. So, no, well, okay. Maybe I won't bother with the board. So the argument runs as follows. So, and this is a verified working pen.
I've got a spare one here.
Perfect. No, Nick, thank you very much. So I'm just going to sort of summarise what's going on here so I can refer back to it. So the initial assumption, so this is assumed for contradiction, and this is that the methods of reasoning that I can use to produce proofs are simulated exactly by M. So M is just some arbitrary computer program, right? We're going to say, suppose that M simulates me, and then we're going to try and show that that's impossible. There's this weasel word in here, so this is just unassailable mathematical proofs. Because you might think that some things that sort of pass muster as mathematical proofs are maybe open to some kind of doubt. So an example of this might be something like the classification of finite simple groups. I don't know if anybody has heard of this theorem, but the proof is like thousands of pages long, and nobody has ever read it all, I assume. So you might think, well, for something like that's an established theorem, but maybe there's some chance that there's an error in there or something like that. So if you're worried about that kind of stuff, Penrose is going to restrict his attention to just unassailable proofs. So these are proofs like 2 + 2 is 4 and things like that, where we're just totally certain that the proof is definitely correct, no mistake, all good. So we're just going to suppose that N is some computer that simulates my unassailable proofs. So that's going to be the thing that we're going to try and show is false. So the output of M has got to match the theorems of some formal system. So we don't necessarily know which one. So if you can imagine, like if you read out a computer program, it wouldn't somehow be obvious what theorems it was eventually going to prove. So we have no idea which formal system M corresponds to, but there will be one of them. One formal system will correspond to it, and we'll just call that T. So there's this. I'm going to write this. This is a slightly weird use of notation. I'm going to write that I equals T as a formulation of the proposition that anything I can prove is provable in this formal theory T, and vice versa. So if anybody is really paying extra good attention, you might notice that doesn't really sound well formed, because what is a theorem that I can prove? But we're already under the hypothesis that M simulates me, and it is well defined what M outputs. So this I equals T idea doesn't really make sense unless I am a computer, but we're assuming that I am. So this can be made good sense of. So the first step of the argument is to just assume that this computer M simulates what I can do, at least as regards unassailable arithmetic proofs. And now Penrose swaps to a proof within a proof, effectively. So suppose that I equals T. So T is just this theory which we don't know, but this may be this corresponds to M, which I'm supposing that I am. So suppose that I is T. Well, what I can prove is unassailably true. What I can unassailably prove is true. So T must be sound. So this is the first step. So effectively, any proposition that I can give an unassailable proof of is correct. So my proofs are true. So T is sound. So the idea is essentially just that Penrose is refusing to admit that he's simulated by a computer that was going to print out a falsehood. And of course, like mathematicians do make mistakes, and occasionally they, did the equivalent of printing out a falsehood. But the idea is that you wouldn't really accept that as an unassailable proof. If there was a mistake, you'd go back and correct it, and so on. So Penrose is supposing that he's always going to prove something true, just so long as the proof is properly unassailable. So now we can define this thing T plus. Right? So T plus is an axiom system that's obtained by adding I equals T as a new axiom to T. So this is a again, this wouldn't make sense if I'm not a computer, because then I equals T is just going to not be like a well-defined proposition. But assuming that I'm simulated by M, that makes sense. So T plus, we're just going to define that as I equals T plus T. So you just add one new axiom. So the next move then is that T plus itself has got to be sound, because it's just T, which we've already worked out is sound, with one extra axiom added, which we're assuming is true. So T plus, as defined, will also be sound. Since it's sound, the Gödel sentence of T plus is going to be true, because we've seen through the standard sort of Gödelian reasoning, the Gödel sentence of T plus asserts that it's not derivable from T plus. Since T plus only proves true things, it doesn't prove G of T plus, but G of T plus encodes the assertion that T plus doesn't prove it. So what it says is true. So G of T plus is true. And then the final step here is to sort of effectively stop assuming that I equals T is true, and we've just got a conditional proof that if I equals T, then G of T plus is true. So this is a sort of A to F here represents a sort of mini proof, and then we can go back to Penrose's main argument. So D, what was this? T plus is sound, and then E is G of T plus is true. So that takes us back to sort of F here, which is if I equals T, then G of T plus is true. So that's the end of the sort of micro proof, and then Penrose can continue with his main argument. So we jump back to the main argument. So by A to F, we've got this proof that if I equals T, then G of T plus is true. So suppose for contradiction that I am T. So this is everything that I can prove is a theorem of T and vice versa. Well, we can define T and T plus just as above, right? And those are going to be sound for just exactly the same reasons as before. So in T, it's derivable that if I equals T, then G of T plus is true. So we know that it's derivable because I've just given this proof here. This A to F, that's a conditional proof that if I equals T, then G of T plus is true. So since I can prove that, under the assumption that I'm simulated by M, M can prove it. So since T is whichever formal theory corresponds to M, it will be a theorem of T that if I am T, then G of T plus is true. So this has the unfortunate consequence that G of T plus is going to be derivable in T plus. So T plus is an extension of T. So this if I am T, then G of T plus is true. That's derivable in T. So it's also derivable in T plus. But now in T plus, we have an extra axiom. So T plus already thinks that I equals T is true. So since G of T plus can derive I equals T, and if I equals T, then G of T plus is true, then we have a proof in G of T plus, or we have derivation in the formal sense of G of T plus in T plus. And this is a contradiction. Right? So we know from Gödel's first theorem that no sound theory proves its own Gödel sentence, and we've just got a contradiction there with T plus will prove its own Gödel sentence. So one of the things that's very clever about this argument is T plus isn't the theory that I am or anything like that. This is a sort of cleverly defined extension of the theory that's supposed to represent what I can do, or what Penrose can do, or what you can do, and we get a contradiction this way. So the assumption that caused the problem, right, was that I equals T. So we've effectively got a refutation of I equals T, but that's a refutation in turn of me being simulated by M. Right? So if I were simulated by n, n really does correspond to some formal theory, and seemingly I've just shown that I don't correspond to this like arbitrary formal theory. So that must mean n doesn't simulate me at all. But then n was arbitrarily chosen as well. So this in turn means that no computer is going to simulate me, because whatever computer you pick, it will be correspond to some formal system T, and then this whole argument, I could just fill in the details and run it again, and this will show that I'm not simulated by that computer. So this is Penrose's idea. Does it make sense? Yeah, people sort of following roughly? Good. Okay, so this is by far the best version of the anti-mechanist argument on the market, I think. I remember staring at it for quite a long time, thinking, there's got to be something wrong. There's got to be something wrong with it. But it's certainly the best version out there. So the next thing to do is to think about where this goes wrong. So this is, as I said, this is the best one. If it works, it tells us something really interesting about ourselves, which is namely that however we're producing mathematical knowledge, it's not the sort of thing that could even, in principle, be simulated by any computer. So I think that would be quite an interesting discovery in terms of like computer science and psychology and philosophy. And it also refutes this possibility of a true AI. So this is an AI, obviously we know that AI can do some maths already, but it seems to refute the possibility of an AI that can simulate all the maths that humans can do. So no matter how good the AI gets, if Penrose is right, there will always be a need for human mathematicians because they can prove some things the corresponding computers can't. Another interesting implication might be, you might think that basic arithmetic and logic is a particularly friendly sort of area for mechanization and simulation by an AI. Maybe not an LLM, we know, but something like chess. We have very good chess playing computers now, right? So you might think this is one of the first areas that the AI people are going to solve properly. Would be arithmetic, but it looks like even arithmetic is off the cards in at least some sense. So that's the sort of interesting part. I suppose, unfortunately, question mark depending on your view, Penrose's argument has a weak spot. The weak spot is what I call, the weak spot relates to what I call the truth premise. So the truth premise is this idea that if I can unassailably prove something, it's got to be true. So effectively, it's this point B, right? So that's the truth premise. So I'm not actually going to take issue with the truth premise. I think the truth premise is probably true. I think I agree with it. Right? There's no chance it's going to turn out that 2 + 2 is 5 or something weird like that. So that's not the weak spot itself. So the truth premise appears in the argument, and I agree with the truth premise. But the issue is that is where the truth premise appears. Right? So the truth premise appears in this little argument A to F. Right? Now A to F is supposed to be a mathematical proof, right? And in particular, it's supposed to be an unassailable mathematical proof, and it has to appear there. Right? So the reason. If we go back to part 3, so A to F has to be a proper proof because we're assuming that, because what we need for the argument, right, is that if I can prove this conditional from A to F, then so can T. Because remember, T is only supposed to, reproduce the things that I can unassailably prove. Right? So if I was only pretty sure of the truth premise, that's not good enough. Right? So because of where the truth premise appears in this A to F, it's got to itself be unassailable, and that's the problem, I think. So this is something we've already touched upon in people's questions, actually. So the problem is what I'm going to call Penrose's premise. So Penrose's premise isn't the truth premise. Penrose's premise is thinking that the truth premise is an unassailable thing of the sort that is fit to appear as a premise in a mathematical proof. So this proof is supposed to be unassailable. If a mathematical proof has a premise that's open to some doubt, I take it that disqualifies it from being unassailable. I mean, Penrose doesn't really define what he means, but certainly it would seem like the argument was open to doubt if one of its premises is open to doubt. So Penrose's premise that he relies on implicitly is that it's an unassailable mathematical truth that what I can prove is true. So Penrose has two arguments for the truth premise, and I think they're both, to some degree, I want to agree, but it's not good enough. So Penrose's first argument is that it would just be really weird, effectively. If we could give a completely unassailable proof of something where there was no flaw in the reasoning, but nonetheless it was false. Right? So if it turned out that 2 plus 2 really is 5, bad luck. No one can spot the error in the reasoning, right, because it's so unassailable. That would be very strange. So I agree that would be very strange, but something being very strange isn't quite the same as it being utterly inconceivable. Human beings are finite creatures, and our power to do arithmetic is finite. And even though arithmetic is kind of the simplest area of maths, the natural numbers are infinite. And you pick, the natural number that counts all of the particles in the universe. That's going to be very big. And there's going to be other natural numbers that are so big that, with respect to that first one, the first one is infinitesimally small. So there are a lot of natural numbers, and I don't think it's, human beings evolved to do maths for various reasons that are related to the world around us, and I just don't think it would be utterly impossible for something to go wrong where we were really sure that a proof was correct and it wasn't. So I don't think that's likely. I agree with Penrose that it would be strange. But remember, Penrose's premise is that the truth premise is unassailable, not just that it's correct. So maybe this gives us some good reason to think it's true, but not good enough reason to think it's unassailable. And his other argument is that when we use maths to create proofs, we're implicitly committed to taking the premises to be true. So this relates to something I mentioned earlier, which is this distinction between just a formal derivation in an axiomatic system and a proper proof that should convince you of the conclusion. Because, for example, producing a formal derivation of anything is really easy. Now, I can produce a formal derivation of the Riemann hypothesis by just having the Riemann hypothesis as one of my axioms and then writing it down again. But that's not a proper proof. Right? The Clay Institute isn't going to pay out if I email that to them. So the idea is, if we're using a sort of formal derivation and we're declaring it to be not merely a derivation but a proper proof where we're convinced of the conclusion, you're implicitly taking the premises to be established truths. And maybe that idea is right again, but again, just being committed to the truth of something doesn't mean that it's actually got to be true, right? If Penrose is right about this, it means that I can't cogently say something like, I have a proof of P, but P is false. I've contradicted myself in some way if I say that. But of course that just doesn't mean that I can't think I have a proof of P, and P actually be false. Right? The fact that I'm committed to the truth of P doesn't mean that P is true. So I'm sympathetic to both of the points Penrose makes, but neither of them is sufficient to establish Penrose's premise, right, which is that the truth premise is unassailable. So even if maybe people will not be convinced, but even if these are enough to convince you that the truth premise is okay, I don't think they should be enough to convince you that the truth premise is unassailable. And in fact, we can say a bit more, I think. So we might want to think of ordinary mathematical truths as properly unassailable. So obviously you can find, for any view you like, you can find some philosopher who's questioned it. But a fairly safe-sounding view is that things like 2 plus 2 is 4, those are unassailable. Those kind of beliefs that you just established in the most elementary way with really short proofs that are super easy and we all know them and there's definitely no mistake there. That stuff you might think is unassailable. It's not open to rational doubt. So that might well be true, but that's not the sort of thing that the truth premise is. So the truth premise, remember this being part B here, right? So if I can give a proof of something, then it's true. So that's not really a straightforwardly arithmetical proposition at all. Right? That's a proposition that's somehow about the relationship between truths and the wider world. So it's effectively a sort of philosophical belief about the relationship of arithmetical beliefs to reality. So even if you think that arithmetical propositions can be unassailable, you probably ought not to think that philosophical propositions about them are similarly unassailable. Right? So famously, philosophers are worse at finding truths out than mathematicians are. Right? If you think about the sort of achievement of mathematics, it's roughly sort of cumulative, like there's a huge body of established theorems, and lots of impressive methods for applying them to the physical world and stuff. Philosophers can't agree on like whether murder is wrong or whether time exists or things like this, right? So philosophical propositions are famously sort of open to doubt and open to debate. So even if you think that mathematical propositions aren't, the truth premise sort of falls on the philosophical side of things, not the mathematical side of things. So to come back to some of the issues that were mentioned before, there are lots of issues, philosophical issues with the notion of truth and sort of defining exactly what it is. Arguably, the standard notion of truth is just incoherent. So has anybody come across the liar paradox before? So the liar paradox is pretty straightforward. And just take a sentence. So this is a perfectly good sentence of English. This sentence is false. So if this sentence itself is true, then what it asserts has to be the case, and what it asserts is that it's false. So if that's true, then it's false. Right? But likewise, if it's false, then what it asserts is actually the case, because it says that it's false. So if this is true, it's false, and if it's false, it's true. That's a contradiction. That's incoherent. So, but there seems to be nothing wrong, with the use of the English language there. There's clearly something fishy going on with the notion of truth. So the notion of truth itself is, in need of some tidying up. Needless to say, philosophers can't come to any kind of agreement about how to do that. So Penrose is straightforwardly invoking a notion that's difficult in the truth premise. And as I said, right, you don't have to start thinking that it's doubtful whether 2 plus 2 is 4. Right? We're not doubting an arithmetical proposition, we're doubting a philosophical proposition about an arithmetical proposition. Another issue, aside from liar paradox type stuff, is related to Platonism. So the view that mathematics is literally true is called Platonism. It's misleadingly called that because it wasn't Plato's view. Or at least that's what a large number of Plato scholars think. But anyway, Platonism is the view that mathematics is literally true. And this is a pretty well established view in the philosophy of maths. So lots of people are Platonists. Gödel was a Platonist as well. But of course, it's up for debate as is anything in philosophy. So to show you what's weird about it, I can give an unassailable proof that there are infinitely many primes. So anyone in this room could give as good a proof as you like that there are infinitely many primes. So what that says is that there are infinitely many things of a certain kind. Right? So if that's literally true, we can start wondering, what are these things that I've proved exist? Right? So infinitely many primes. They don't seem to be like physical objects. Right? So if you start asking questions involving physical properties about primes, you're just going to get weird stuff. Right? So it doesn't seem to make any sense to ask what the kind of mass of a prime number is, or where it's located in the universe, or what colour it is, or things like that. So it seems like whatever these prime numbers are, they can't be physical objects. A tempting move might be to say, maybe they're like mental objects, right? They're something that we've sort of imagined, but there are infinitely many of them. I've only got finitely many brain cells and so on, so it seems like there's not enough room for all the primes in my head, as it were. So most Platonists will tell you that the numbers are abstract objects. Right? So they exist objectively. So they're not mental entities. They exist objectively, but they're not spatial or temporal. Right? They're just doing their own thing. They're just mathematical objects. Now, it might be true or it might be false that there are infinitely many abstract objects. But I think, hopefully, we can all agree it's not unassailably true that there are infinitely many abstract objects. Right? Loads of people, for instance, only believe in physical things. So if the truth premise were really unassailable, we would have a knockdown proof that those people are wrong and that some non-physical things exist. So whatever you think of Platonism, maybe good, maybe bad, there are obviously arguments for and against, it doesn't seem sort of unassailably true. And that's the problem with Penrose's premise. So Penrose has this argument for a contradiction that some arbitrary computer simulates me, very clever, but it has this mini-proof, and in the mini-proof is a truth premise. The truth premise is probably okay, but the truth premise has to be unassailable to appear where it appears in Penrose's argument, and that, I think, is pretty much untenable as a position. In light of the liar paradox type stuff, and issues to do with Platonism, and numerous other things that we could mention. So returning to the original question, Gödel's theorem does tell us something substantive about AI. What it tells us is that no AI which is based on the classic Turing machine model of computation can prove all and only the true theorems of arithmetic. So we could get an AI program that proves all the truths of arithmetic and loads of false ones, or we can get it to only prove true things, but not all of them. And I think that is already quite an interesting result. But there's no clear route from that fact to a refutation of the entire sort of project of simulating mathematicians using machines. So, as I said, I think Penrose's argument is the best one. I think probably anyone who knows the literature would agree with that, but unfortunately, it doesn't work. And as I said, the main problem is that it fails to respect this distinction between arithmetical beliefs, which are the sort of things that you might, are amenable to proof, and that you might even be entitled to complete certainty regarding them. But philosophical judgments about those beliefs are necessarily more speculative. We are not entitled to be certain about them, and that's the slip that Penrose makes. So there we go. That's the end. So we still don't know if mathematical truth rules out the possibility of AI, but I don't think Penrose has shown that. So thanks very much.